Today we look at the wonderful topic of insulation. Excellent. We're going to look at this, and in order to solve that or solve problems about insulation, we're going to use our knowledge of conduction, convection, and radiation. Okay, so just as a kind of reminder before we, what are our sort of fundamental principles of these various things? So we have. We've got conduction, which happens in solids. As basically metals really well. This is terrible English. Okay, we've got convection, which happens in fluids. Okay, and we've got radiation, which is waves of energy, and is in some way color dependent. Okay, so this is what we have. This is how they happen. The question we've got to ask ourselves is, okay, how do we slow it down? Okay, how do we stop it? Well, conduction. We want to avoid using metals. Okay, so if you've got to use a solid, use a plastic. Okay, if you can get away with it, have gaps. Have sort of like breaks in the solid. So air gaps, can you? Because if there's no solid, there can be no conduction. So that's going to be the principle we're going to play it if we want to slow down conduction. Convection happens in fluids. Fantastic. Best case scenario is remove the fluid. Which is called a vacuum. Because, by the way, fluid, remember, doesn't just mean water, it can mean gases as well. So if we can have a vacuum, we have no convection. Not always possible. Very rare that you're sort of in a place going, oh, you know what would help stop the convection current in this bath is to not have any water. Not always helpful. Might be a bit tricky. So sometimes you just got to have the fluid anyway. What we can do is we can stop it. We can sort of try and stop the fluid from moving. Okay, if we can trap it, then in a space, then yeah, it's still going to have a convection current, but it can't go anywhere. It can't leave entirely. Final way is radiation, color dependent. Well, hopefully you remember. Use light colors. Okay, that's how we solve. So these are the principles. So we're going to look at a few sort of examples in everyday usage before we worry about exam questions and so on, and try and break it apart and see what we can have in various ways. So let's look at these fine people who I found on a stock photo website. What have they done? Well, they're either terrible superheroes or they've just run a marathon. And anytime people run like long distance things, even I do, and I'm not very quick, you tend to get over the line and they wrap one of these weird foil blankets around. Okay, why do they do that? Aside from it being a wonderful fashion statement. Oh look, it's 2010. Is that the Boston Marathon of 2010? My goodness. Well, it's to form a little insulating layer. Let's think about why do you suddenly need this kind of thing after you've been running, even somewhere where it's quite hot? Well, if you run around a lot, okay, so if you're sort of running around and you're running around literally for several hours, you're going lots and lots and lots and lots of times. Well, your body just works harder. You will notice that you are going to be flushed and you're going to feel like you're radiating more because your body, by running around for ages, your body is going to essentially acclimatize itself to saying, oh no, I need to dump more heat out. And you may have done this in biology. Your vessels near the surface of your skin open up to release more, try and radiate more energy, which is why you sort of look flushed. You're not glowing red because you're really, really hot. You are glowing red because the blood's rushing to the skin surface. You know, you're sweating more. Your body basically acclimatizes. You're on a marathon. You're running for 3, 4, 5 hours at a rate where you're kind of balancing the extra thermal energy that's being created by all your activity with getting rid of it into the atmosphere. When you stop, your body isn't ready for that. You might know in your brain that you've stopped, but this order is automatic. It's an automatic response to increasing temperature. So, well, what happens is that you stop, and your body isn't aware. It's still going to be working hard, and it's still thinking, I've got to dump loads of heat in. What's the risk of that? The risk of that is your temperature drops very rapidly. Now, most of the time, actually, people who are sort of like good or decent athletes and they're kind of used to it, your body will acclimatize reasonably quickly, but you come over the line and you start feeling very cold. So what do? Well, we wrap a foil blanket around you. So we cover you in a sort of foil blanket. Now, if we zoom into what that means, that means that any sort of attempt you're going to have of radiating energy out, the reason it's foil, you're going to radiate energy out, but that energy is going to get radiated back at you. So the silver nature of it means that you're going to, any radiation out gets reflected back. You might think, oh, but what happens about the fact that it's wrapped around you? Aluminium is a good conductor. It's going to get warm as well, and that's true, but it's silver, so it's a poorer emitter of radiation as well. So by being wrapped in a silver blanket, you aren't emitting as much radiation, or it won't emit much radiation, so it stays warmer. The final thing it does, and I might need to draw this again slightly, is a person who is sort of like exposed to the elements. One of the other ways in which you sort of lose energy is that you will warm the air around you, so the air around you becomes warm, and it will then have a convection current, so it will vanish off to be replaced by, oh yes, colder air. That's bad. That air, gone somewhere else, not coming back to you, okay? But if you have a silver sort of foil blanket around you, well, you've trapped that convection current. That air, when it's warmed up, can't escape forever. It can go sort of to the top of the blanket, and then it's just sort of stuck. And so you're going to insulate yourself with a nice cushion of warm air around you. And as that air warms up, the convection current, well, yes, there's still a convection current coming in it, but it's not going anywhere. It's just trapped inside, your blanket of awesomeness. And because this hot air rises, it's actually irrelevant, even if you don't have it completely sealed up at the bottom, because all you're going to do is just warm the air around you and make yourself a nice sort of insulating layer. This person's trying to wear a very, very strange coat. So this is how something like a tin foil sort of sheath can work. And given, people, when you finish a long run, you end up with, taking on lots of sugar, your body will eventually quite rapidly work out that it's no longer running, and it'll be like, oh, thank goodness, I can stop, and I will be more calm. But even that's one of the reasons why those things are there, and they're cheap. Even in nice warm weather, or pleasant weather to run in, you will notice that kind of temperature drop when you finish. And it's also one of the reasons why it can become quite hard if you stop to start again, because your temperature will drop quite quickly. Right, there's one version. Let's look at, fantastic. Let's look at buildings. This is cavity wall insulation. Okay, so this is an example of what we call cavity wall insulation. Oh, you do not ever need to, by the way, you don't need to remember all these things. What you need to be able to do is to explain how conduction and convection work. The cavity wall insulation is thus. Okay, this weird foamy stuff that sits in between two layers of bricks. Most houses are not one single layer of bricks. So the outside layer of your house is not one exposed layer of brickwork. Okay, quite so much. What will tend to happen as well is you have an interior layer. Now, for a long time, that's kind of all house walls were. And one of the reasons for that, as well as being structurally more sound is it meant that actually if you had, say you're inside, this is our inside and this is out, it's cold here and it's warm here, then what would happen, if you only have one layer, then what you would just get is eventually you'd get sort of a conduction through the solids of the brickwork and then out to the outside of the thing. Having two layers, help out the whole thing. Not only are you building a stronger wall of better foundations, but by having two layers, you've got a second layer. Fantastic, because then what you'd have to have is a conduction. Then in this air gap, you would have to set up a convection current, which is slower, and then you have to conduct again. So what happens is you get a much slower movement of thermal energy from inside to outside. However, problem with these sort of cavities is they're really big. You can look at them; they're quite sizable, and they'll go all around the house, and it's quite capable of setting up some really big convection currents over the whole house. And a big convection current is still able to move a lot of thermal energy around. It doesn't just need to move; it's not about moving it to here. It's about moving it into this brick wall here, because then that means that this brick wall will get cooler, and so you lose more energy. You're not terribly happy if the inside of this wall is really nice and toasty. You want, because you're losing your thermal energy. So what do we do instead? Well, we now inject this stuff into it. And you can actually get this stuff, even on old houses, you can get this stuff injected into like things. And you might have seen stuff like it. It's a big foamy substance, okay? So if we zoomed in on it, what we'd see, I'm going to use the rainbow. So we inject this kind of weird, that little dottiness in this place. Imagine those little light dots, air pockets, okay? It's a great coloured pen for it. It's a pity that I've just made it look like a bit of a splurge on this whole thing. So what we have are these little weird air pockets. And the thing about air is, so it's not a solid that's connecting the two things. It's basically something which is very low density. It's got lots of air pockets in. And so what happens is if you get sort of, so you've got a bit of a solid, but then you've got a sort of an air pocket, and then you've got a bit of solid again. When the thermal energy comes through, goes from here into here through conduction, well, what you get is a convection current, but it's got nowhere to go. It's a very, very tiny one. It's very inefficient. Can't take the energy anywhere other than where it is. So what happens is you have conduction, but then you've got to do convection over this little gap, and then you've got to do conduction again. Then you have another air gap, and then you've got another bit, and then you have another air gap. And every time there's an air gap, you've got to set up a convection current to get energy from one side of it to the other. That makes it really slow. So this is also why things like woolly jumpers are warm. It's because you have something that traps little pockets of air, and it enables, and convection through a trap pocket of air is really, really slow. And that's how things like this work. You find it in loft insulation. You find it the same thing if you wear 3 t-shirts. You wear 3 t-shirts, you're going to trap layers of air between each t-shirt. That's going to keep you warm. It's one of the fundamental reasons why when you're cold, people tend to put another layer on. If you're going out and it's cold, people will put another layer on. And that is the thing there. So that's it. Now the other alternative. So this is where we can't remove the air from inside it. It will collapse our building. But there are places where we can do that, and this is double glazing. Double glazing is a very similar kind of idea. Okay, by having a trapped layer of air, you are going to make it so that you don't just have to have one kind of conduction, but you then have to set up a convection current, and then you have conduction again. And that is so slow. But what we can do is actually, in many things, we can actually remove air from the gap. By removing air from the gap and making it close to a vacuum, suddenly there's not many particles to move around here to take this from one side to the other. So the actual secondary layer in here, by removing air from the gap, which is one thing we can do, we can slow convection down even further. And this is the next thing that we can do. So the idea, we've got a thermal energy transfer going from It's going this way. Now you've obviously still got a window there, which means that what we've got is the ability for radiation to work as well. The radiation will still pass straight through, but I can't do much about that because I do want my window. I want to be able to see outside. So we have to, if we didn't want to do it entirely, we just have a brickwork. But we do kind of like windows. So what we have here is, we'd have a convection current set up inside the room, which is making this interior wall glass warmer. We then get some conduction through, then convection through, and then we'll get convection current, which will carry thermal energy away. You can get triple glazed glass, but the added efficiency isn't that much greater, so it's not really a great thing to do. Let's see. Let's look at the last sort of big example, the thermos flask. This is an example of a thermos flask in action. This is a sort of a cutaway of one, and this is kind of what it looks like. Now, thermos flasks, or Dewar flasks, are designed to keep liquids hot or cold, which if you've ever used one, you're really, really, really good at it. But the other thing you might notice is there's not anywhere near as much space on the inside of the fluid as you might think, given the size of the bottles. And that's because they are covered in things to stop their being, to stop thermal energy transferring. So let's imagine we've got a really hot kind of liquid inside. So this liquid is really hot. So let's imagine that's hot. So we want to normally lose thermal energy to the cold exterior. But what are we first going to come across? Well, the first thing we're coming across is an interior layer that's silver, which means if this liquid is radiating thermal energy away, well, that's going to get reflected back. It's going to stay inside. Fantastic. We are, however, going to warm up that interior liquid, that interior layer of that silver thing. We're going to warm it up because we're in contact with it, so conduction is going to warm it up. But what has it then got to pass through? Well, this gap here, this is a vacuum. There is no air in here. This is no air. So what can't happen in there? We can't have convection. Cannot set up a convection current. Cannot have conduction because, there's no solid, there's no liquid, there's no gas. So both conduction and convection are out. So our only method of crossing this barrier is radiation. But look what the second layer is. The second layer is also silvered. So much I think you'll radiate across, but then it will radiate back. And you just you're going to trap radiation bouncing around between these mirrors for ages. Eventually, it still will get across, which is fine. It's acceptable. It does happen. So what do we cover the whole thing in? Well, we'll cover it in some plastic. A nice non-metallic, conductor around the top to make sure that it's even slower. So we'll use a plastic. You might find that some have a silvered outer layer just for preference rather than anything else, or it adds a final layer to stop radiation happening on the very edge. But that is how vacuum flasks work. So in each and every one of these cases, all you have to think about every time is where is the hot thing? Where's the hot thing? Where's the cold thing? And then think about what you're putting in the way between the barriers. Are you putting in layers of plastic or air gaps? In which case, you're stopping conduction. Are you having bits where we're either removing the air or removing the fluid, in which case a vacuum, we're stopping convection and we're stopping conduction? Or are we going to have trapped bits of air to stop things moving around? Well, that's convection. And then finally, are we going to use silvered layers anywhere in order to stop convection? That beeper is something else, but that is, thankfully, at the end of this little talk. You never need to recall all these things, but we will see now some examples of practice questions where they are in play.